Alright everybody, this is section 11.1. It's the chi-squared test of independence section. So this crazy looking, I know a lot of you are going to say x squared, but this is actually the Greek letter chi squared. It has these different features that we're not quite used to. So all the values are going to be positive no matter what, because we're going to end up squaring things so that they're positive, hence the chi-squared part. Distribution is determined directly off the degrees of freedom. Everything is skewed right. Okay, so everything's going to be, it's going to get close to bell shape, but not quite. And then n minus 2 is the smallest number we can have because we need to have samples greater than 3. So we'll kind of talk about that. So as the degrees of freedom increases, so as your numbers increase, your chi-squared tends to become more bell-shaped. But usually we're going to be with smaller degrees of freedom, so it's going to be definitely heavily skewed right. So that's kind of something to keep in mind. And we'll kind of look at a few more examples in a second. So just a few things to note. When you start adding these things up and you get a smaller number, okay, that is directly based off of these numbers down here. These are your chi-squared numbers. The smaller you are, you're not very far away. And everything in there, your table, we're used to like the z table being everything to the left. Well, chi-squared's backwards. It's everything to the right. So when you get a number less than 1, it's like the area in here. That's most of your curve. So if you look at the table, if you have the table that I gave you, and you look at degrees of freedom of 3, okay, and you look at a small chi-squared number like 7% or something, we have 99.5%. Okay, that's the area to the right of the line. So it's a little bit different. It's everything to the right. And then this becomes our p-value because this is a statistical test that we compare to our alpha. So if you actually have a larger number, so if your chi-squared number happens to be like 13.28 for a degrees of freedom of 4, that's the other one I have highlighted. Okay, if you end up have that, then your p-value, okay, would end up being 0.01. It's going to be an exact number. So then that would be very small or significant. So basically in hindsight, if your chi-squared is a big number, it's very significant. The observed to the expected values are a lot different. If it's a small number, probably not as significant. Okay? So test of independence is what we're doing. It's going to be a qualitative variable. So instead of actually having quantity, we're going to do qualitative. We're testing if something's independent from the other. It's kind of like a yes or no question. Okay, you still need a null and an alternate hypothesis. So your null hypothesis is always going to be that they are independent, that there is a difference, okay? And then the variables are not independent would be your alternate basically every single time. Okay? Every single one of these will be presented in a contingency table or some type of box or table with rows being one of the variables and then obviously the columns with the other one. So here's an example. So we're going to look at what kind of keyboard one uses and learning how to type, and we're going to see if these things are independent or if the keyboard really does depend upon how fast you type. Okay, so the keyboard style, okay, is keyboard A, B, and then standard, and then the number of hours that you actually practice or how long it takes to get to a certain level is in the columns. Okay, so these 9 numbers are the ones we're going to focus on a lot. And this is the observed amount. This number is what has been observed. So if they use, keyboard A and then the number of hours to learn how to type, so 25 hours is the observed. 25 people needed that long. 30 people needed 41 to 60. 25 people needed 61 to 80 with that particular keyboard. And then we're going to kind of compare and see the difference. Okay? So how would you set this test up? So you're going to state in your alternate or in your null hypothesis that the keyboard and the number of hours are independent every time you set up the null to be independent. There's no relationship at all, and we want to try to prove that there is a relationship there that's needed. Okay? The alternate's going to be whatever we're talking about, keyboard style and number of hours, to be not independent. Okay? You still have an alpha, so that part's not changing, but what we need to do is calculate the expected value. Being independent is seeing if there's a big difference between what's actually happening, the observed, to what is the expected. How does the expected work? You need your row total times your column total divided by the sample size. Okay, so just a quick example. If we look at just the first box, the expected value for the first box is the row total, 90, times the, I lied, that's the column total. So row total is 80 times 90 divided by your sample size. And if you multiply that out, that's your expected value. So I actually do that right here. So 80 times the 90 divided by 300 gets you 24. So the expected number in this box is 24. We found out that there was 25. The expected value for the number 2 cell. Okay, so we have 80 times 150 divided by 300 is 40. So we expect 40 there. Okay, we actually had 30, so there's a little bit more difference. So you will continue on to do this. So you would take, for number 3, you would end up, the expected is 80 times 60 divided by 300. Okay, and whatever you get out of that, that would end up being your answer. And then so on and so forth all the way down. So then if you go to number 4, you would end up with 120 times 90 divided by 300. And you would need to calculate that expected value every time. Alright, now what does the chi-squared number? So essentially this is your, if you want to think about it back to other tests, this is like your t-statistic. Way back in Chapter 8, Chapter 9, Chapter 10, except now we are converting it and it's a chi-squared statistic. Okay, we had so many formulas used to find this one. Now this is our formula. Alright, this E-looking thing is called the sum, and then we need the observed minus the expected number. You just found the expected numbers, you square them, and then divide by the expected once again. So here's kind of a table that I use all the time. So I'm only looking at the first 4 boxes here. I don't really want to do all of them because it would take too long just to do this on the video. But we said our observed number was 25 and the expected was 24 for the first number. So 25 is the observed, 24 is the expected. You subtract them, get 1, square it, still 1, and then divide by 24. 1 divided by 24 is 0.04. And then you keep doing that all the way down for each particular cell. Since this is a 3 by 3 area, you will end up having 9 of them. 1 for every single box. So then my observed is 30, expected is 40, negative 10. You square it. That's why everything's positive. Even if you get a negative number, it'll become positive. Divide by your expected. And then you will end up getting 9 numbers in this column. The sum, this guy, is what you do with this ending column. You add all 9 numbers up, and if you actually practice or do that, you would end up getting 13.31. That's your chi-squared number. Okay, so there's no good way, no shortcut to this. This is literally what you need to do. Build the table, do what the formula says, and the formula is on your formula sheet. If you look at the Chapter 11 formulas, it's the very first one. You have to do this. Alright, no shortcuts in this chapter. I'm not going to tell you that anything in class. So you have to do all 9 boxes, add them up, and you get that chi-squared number. So the chi-squared number does no good unless we know the degrees of freedom. Now degrees of freedom is a little bit different. You need to multiply the row minus 1 times the columns minus 1. Now where do I go to do this? You look at your contingency table. This table is a 3 row by 3 column contingency table. 3 times 3 is 9, so kind of the same number. So 3 by 3 is what I have. So that's why when I go in here, it's 3 minus 1 times 3 minus 1. 2 times 2, degrees of freedom is 4. So then you now have your information you need to finish your test. Okay? You have degrees of freedom is 4, and what we need to do is figure out where does my test statistic fall between. So this is exactly like the t-score in your t-table. You have an answer, figure out what 2 columns it falls between. So 13.31 at degrees of freedom 4, if you follow over, you should see that it falls between the end 2 columns on your table. So then you end up building an interval. No different than we've done before. So this, hopefully at this point, is nothing new. You should be able to build your intervals between 0.005 and 0.01, and you finish your test accordingly. Okay? So how do you finish the test? Everything that we have ever done before. So I just want to talk about this one more time. So in test of independence, a right-tailed test is always used. So you look at everything to the right. So exactly what's going up on the top of your page is what's in the right tail. You're testing to see if there's a difference between those observed values and the expecteds. Okay, we're seeing if it's too large to be just sheer chance alone. Okay, and since the p-value in our example, we're going back to the keyboard, you're less than alpha, we reject the null. Okay, which means that the variables are not independent. So there is what you're saying is that there is a relationship, okay, between the keyboard and the number of hours typing, but you don't necessarily have to state that. Here's how you need to do it. Okay, so at the 5% level, the keyboard style and the number of hours learned typing are not independent. There's some type of relationship there. It's probably easier to type on the way our keyboards are set than if you would put the alphabet out in order or something like that. So that is one example from top to bottom on what we do with the chi-squared test of independence. This is the assignment we're going to work on in class, and hopefully you all have a great day.